Thanks for the invitation to speak here. Um, yeah, so as Yifei said, my research is mostly in algebraic combinatorics, which sort of means two things, right? It could mean using algebraic tools in order to study combinatorial objects, or vice versa, using combinatorial tools to study algebraic objects. And so for us today, I'm mostly going to focus on this first approach, where we're going to study some discrete objects using some algebra, namely using polynomials. Okay? And so we're going to use some polynomials to study graph colors. So maybe let's fix a definition of, and make sure everyone knows what a graph is, as this will be our key object for the rest of the talk. So for us, the graph is just going to consist of a finite set of vertices or nodes and a finite set of edges or arcs between these vertices. And I sort of made this definition big on purpose. And the reason being that at the heart of what this is trying to do is it's really sort of a data structure in which we care about the pairwise relationship between our data points. So for instance, maybe we want to model like a social network where we have like a bunch of people, which is our vertices, and we care about whether people are friends or not, which is like an edge between. Or maybe we have like some metro system where like the stops on our metro are like our vertices, and then we care about whether or not there's a connection between them. So there's lots of different types. So for instance, on the left, we have a simple graph. So here we have like a bunch of vertices or nodes, which I've labeled by numbers. And then we have a bunch of connections between these nodes, right? And we just care about whether there's a presence of an edge or not. Okay. So this is like a simple graph. Then we could add multi-edges and loops. So a multi-edge just means between any two vertices, we allow for multiple edges between the vertices. Okay. So maybe this would be like the setting of like a metro system, maybe, or like a stop or cities where there could be multiple routes between two different locations. Okay. And then a loop is just an edge from a vertex back to itself. We could also have directed edges, giving us a directed graph. So here we see that all of the edges have an arrow on them. So in this, we not only care about whether or not there's a presence of a relationship, we also care about the direction of the relationship, right? These could be like states in like a Markov chain in which we care about um, how we could jump from one state to another state at any given time. Okay. But for our talk, we're really only going to care about simple undirected graphs. Okay. So as we'll see in just a little bit, I'm going to care about graph colorings and specifically vertex graph colorings. And these don't really care whether or not we have multi-edges, loops, or directed edges. Okay. So for us, we're just going to omit them, and we're going to look at the most easiest case. We have no multi-edges, no loops, and no directed edges. And I should say, feel free to ask any questions in the middle of my talk. Okay, so what is a coloring? So a proper coloring, or just a, well, okay, a coloring in general is just an assignment of colors to the vertices of our graph. And it's proper if two adjacent vertices are colored differently. And by adjacent vertices, I just mean that they share an edge. So for instance, let's consider this graph here. And we're going to assign colors to each of these vertices. So maybe let's say that we colored this graph as follows. So we colored this vertex 1 with the color red, this vertex 2 with the color blue, then 3 with green, 4 with purple, and then 5 with red. And so if we look at this, we see that it's a proper coloring, right? Because along every edge, the two vertices are colored differently, right? So along this edge here, right, I have red and green, so they're colored differently. And then here I have red and blue, they're colored differently. But whenever I do not have an edge between two vertices, for instance, let's say vertex 1 and 5 do not share a relationship, then I'm allowed to color them the same color. So here we're thinking about our edges as like some sort of constraints on our graph. Okay. So maybe let's give an example of an improper coloring. So this is improper, right? Because along these two edges here, these vertices share the same color. So more specifically, we also care about the number of colors that we use. So a proper K coloring of a graph is a proper coloring with at most K colors. Okay, and we will say that our graph is K colorable if such a coloring exists. So for instance, in this example here of this proper coloring, we've only used four colors, right? We've used red, blue, green, and purple, and this gave us a proper coloring. So this is a proper four color, meaning that this graph here is four colorable, right? Because we were able to find a coloring that only used, a proper coloring that only used four colors. But do note that in this definition, I say that we only require at most K colors. So this proper four coloring is also a proper five coloring, a proper six coloring, etc. Okay. These are like the colors that we have, or the number of colors we have at our disposal, but we don't have to use every single one of them. Okay. This is like sort of a bound of the number of colors, but not a requirement. So because of this property, where like a four coloring is also a five coloring, is also a six coloring, etc., we really mostly care about the smallest number k that actually works. Okay, and we give this a special name, which is called the chromatic number. So the chromatic number of a graph is the smallest number k, such that our graph G is k color. So maybe let's look at our graph here again. Maybe I'll give you a minute or two to, to see if you can find the smallest number of colors you need in order to color this graph.
Maybe it's three. I don't know. Yeah.
Perfect. So let's try to argue why it's three. So we saw on the previous page, right, we could color it with four colors. So obviously we have an upper bound of four, right? But it could be the case that we could do better than four, right? So here, this is an example of a three coloring of this graph, but note that it's proper, right? Along no edge is any two vertices colored the same color. Okay? And so now why can we do no better than three colors, right? This is sort of an upper bound, but maybe it is possible to color this graph with two colors. But the problem is, right, we have these triangles in our graph, and along every triangle, note that we have to use at least three colors to color it. Or we have to use exactly three colors, right, along any triangle. So this also gives us a lower bound, meaning that our chromatic number for this graph is exactly three. So in general, finding the chromatic number of a graph is in general hard, but it is possible for special families of graphs. So maybe let's go over a couple just to solidify this concept. So for instance, if we look at complete graphs, so these are graphs in which every possible edge is present. We see that the chromatic number of these complete graphs is equal to its number of vertices, right? Because we have to use a different color for every single vertex. So if we look at trees, right, the chromatic number of a tree is always two if it has at least two vertices. And if you've never seen a tree before, trees are just connected graphs that have no cycles in them. Okay. So why might this be true? Well, I claim that we can sort of peel off one of these extremal vertices as follows. You can imagine that we peeled off one of these smaller vertices. And so we get a smaller tree, and so we can sort of inductively do this. And so if we have a two coloring of this smaller tree, then because this vertex here is only connected to one other vertex, then we can just color this vertex the color that wasn't used for this other vertex here. So we can sort of build up this coloring, and we can show that this coloring is always, it can be colored with two colors. How about for cycles? So cycles, there's like two cases. It's either two or three. And the reason being, oops, that so if we have an even cycle here, we can just alternate between like red, blue, and that gives us a proper coloring. But the problem is if we have an odd cycle and we do the same thing of red, blue, red, you see that both of these two vertices here are colored red, which is bad. So we need a third color. And probably the most famous result is with regards to planar graphs. So these are graphs in which you can draw them on the plane such that no two edges cross. So for instance, this graph up here, which is K5, I claim that there's no drawing of this graph in which no two edges cross. So the four color theorem states that for any planar graph, we have an upper bound of four. Okay? But this is not necessarily what the chromatic number is equal to, it's just an upper, right? And it clearly can't be exactly the number, right? Because like trees are always planar. Trees are always planar and cycles are always planar. But they achieve a lower chromatic number. So what are some applications of these chromatic numbers? So maybe let me give two examples. So these often come up in scheduling problems. So these are problems and where we want to minimize the number of time slots needed for competing or conflicting activities. So maybe let's give a toy example or a toy problem. So let's say that we have a set of experiments that need to be made at an observatory, but only one experiment can be made at any given time. Okay? Meaning that we can't have two experiments that overlap in their start and end date um, be run at the same observatory. So for instance, here, experiment A runs from September 2nd to January 3rd, but it overlaps with October 15th through March 10th, right? So you wouldn't be able to run both of these experiments simultaneously at the same observatory. So the question is, okay, what's the minimum number of observatories needed to perform all of these experiments? So how could we possibly model this as a graph coloring problem? So we're going to model each experiment as a vertex, and then what are our edges? Well, our edges are like our constraints, right? Because our edges play the role of constraints on our graph colors. Okay. So for instance, I claim that this is the corresponding graph to this problem. And why is that? Well, as we saw earlier, experiment A overlaps with experiment B, so that's why they share an edge. And experiment B also overlaps with experiment C, so that's why they share an edge, and so on and so forth. Okay, so we have an edge whenever two experiments overlap. Okay, so how could we solve this problem? Well, this problem of finding the minimum number of observatories is exactly the same thing as finding the chromatic number of this graph. Oops. Okay. So this is one place where the chromatic number shows. Let's look at another example. And for this example, this is going to relate to sudoku. So maybe let me pull up our sudoku board. So if you've never played Sudoku before, these are like logic puzzles where you need to place the digits 1 through 9 once in every row, once in every column, and every 3 by 3 blocks. Right? So for instance, and then you have to use logic to sort of fill in the rest of the grid. So for instance, if we look at this grid here, we have a 4 in this box and a 4 in this box. And both of these 4s peer into this third 3 by 3 box in this upper right-hand corner. Meaning that the 4 in this 3 by 3 box can't be in the second row and can't be in this third row. So a 4 has to be between the 9 and the 1. Okay? And using sort of these logical principles, one would have to fill out the rest of this grid. Okay. So our question is, okay, given an arrangement or assortment of numbers, is the Sudoku puzzle valid? Okay, so is it possible to logically fill out this grid uh, in a single way? Okay. So how could we model this? So for us, we're going to think of every box as a vertex in our graph. Okay. So for instance, we'll have 81 vertices in our graph. And we're going to connect vertices that are in the same row, same column, and then same 3 by 3 box. So for instance, this vertex 3 is connected to all of these other vertices. Right, so this circle here is connected to every single vertex in this 3 by 3 box, every single vertex in this column, and every vertex in this row. And then we'll draw edges between them. Okay, so here I've only drawn the edges between this vertex and the vertices in its column. But if you can imagine, there's a lot more, right? This vertex would connect to every single vertex in its row, 3 by 3 box, and you would do this for every single other vertex as well. Okay. And so what about these numbers that are already populated our grid? Well, we're going to think about these numbers that are in our grid as sort of pre-colored vertices, right? I'm thinking about this vertex as like colored by the number 3 already. So the question is, we want to show that the pre-color vertices in our grid can be extended to a proper 9 coloring, right? And that there's exactly one such color. If this is supposed to be logically solved, there should only be exactly one solution. So we'll see a method in order to solve both of these problems of like scheduling and Sudoku. Now, this might not be the most efficient algorithm, but it is an algorithm that one could code. And so to do this, well, we'll pass to algebra. So Berghoff in 1912 decided to associate a polynomial to these graph colorings. And really, he was interested in proving or trying to prove the four-color theorem. It turned out that this wasn't the correct approach to solving the four-color theorem. This is sort of interesting in its own right and will help us solve these two applications that we were looking at earlier. So the chromatic polynomial of our graph is defined to be the polynomial satisfying that whenever I plug in a non-negative number k, I get the number of proper k colorings of our graph. So this is already weird, because normally when you see polynomials, right, we are usually given the coefficients of the polynomial. But here I'm not giving you the coefficients of the polynomial, I'm just specifying what the values are at the positive integer values, and really also at the point 0. So let's see an example, because from this definition, it might not be so clear what's happening. So let's look at this path graph on 3 vertices. And let's try to figure out its chromatic polynomial. So we need to figure out the number of proper k colorings of this graph. And so if we try to do this, well, if I have k colors available to us, then I have k choices of what to color this first vertex, right? I have k choices of what color to assign to this vertex 1. But once I've assigned my color to this first vertex, now I only have k minus 1 choices of how to color the second vertex, right? Otherwise, because this vertex here is taking up one of the colors that 2 could use, we only have k minus 1 possibility. And then how many possibilities do we have for 3? Well, we also have k minus 1, right? Because 3 only has one edge. This has a color which this vertex 3 cannot use. So our chromatic polynomial is given by k times k minus 1 times k minus 1. And so we see that it is indeed a polynomial. And let's just do a sanity check. So for instance, if I plug in 0 and 1, I get 0, right? There's no way to color this graph with 0 colors. Okay, that's sort of the trivial case. And there's no way to color this with exactly one color, right? But when we get to 2, and I plug in the number 2 into our polynomial, we get that this is 2 times 1, which is 2. And this should tell us that there's two ways of coloring this graph with two colors, right? And we can see that here. You can do red, blue, red, or blue, red, blue. So this is what our polynomial is trying to tell. So maybe let's look at these graphs. So maybe let me give you a minute to think about what's happening here. And just figure out what the chromatic polynomial. Well, hopefully that was enough
Yeah,
time
so
to
the
at least maybe.
right.
Oh yeah. Do you have it?
Well, for the first one, the at the first node, number one will have k colorings. So and number two will have k minus one, and number three also k minus one because connected to number two. Now at four though, because it's connected to other three, so it will be k minus three. Wait, oh no, it's not k minus three because the other two, one and three could be different or could be the same. And one and three could be the
Yeah.
same. Also for that one, is it simply k minus two then? But I guess probably not. Or it would
Yeah.
be
So
case.
what you just illustrated is that it sort of depends on how we go through it, right? And it's not so easy as our previous example.
Right, right.
So for us, it turns out it's actually easier if we color this first triangle first.
Uh, okay.
So here we have k choices and then k minus 1 choices. And then rather than doing 3, so I sort of tricked you by putting this 3 here. So you actually want to do 4 first. So there's k minus 2 choices
Right,
here, right? Because it shares a color or an edge with k and k minus 1, or
right. The
vertices 1 and
three
2.
will right. The third one will just be k minus two.
Yeah, perfect. So we get k times k minus 1 times k minus 2
Mm.
squared. But what exactly what you were saying, we actually have to do for this cycle. So if we try to do the same thing of like k minus 1,
Hmm.
k minus 1, and then we sort of have a problem in that, okay, whether or not these two vertices are colored the same way. So for this graph, we actually have to break it up into two cases, right? Whether or not these vertices 2 and 4 share the same color.
Hmm.
And then using this casework, one could figure out the chromatic polynomial. Okay. So here we have k choices for vertex 1, k minus 1 for 2. And because we're in the case that we're assuming 2 and 4 share the same edge, we don't have to care about what vertex 4 is colored. And then we have k minus 1 choices here. Okay. And then case 2 is similar. Okay. And so just as before, in general, finding the chromatic polynomial is hard, but for certain families, it's doable. right? So we have the complete graph, which is like k times k minus 1 up until k minus n. We have trees, which is like k times k minus 1 to the n minus 1 if it has n vertices. And this can be proven the same way if like peeling off leaves of your tree in the induction. And then we also have cycles, right? And this minus 1 to the n is sort of coming from the fact that odd cycles or even cycles and odd cycles have different behavior. But there's a question of, okay, how do we compute this in general, right? If I give your graph to a computer, how would one solve it? And then the second question is, why is this even a polynomial to begin with? Hey, we start to see that it is in these examples, but why is it in general? And so this comes from this fact of this deletion contraction form. So to do this, I need to define two notions. One is this notion of an edge contraction. So, and one is this notion of an edge deletion. So given the edge in our graph, we say that we can contract the edge if we just identify the endpoints of the edge together, and we delete the edge by just deleting the edge or removing the edge. So for instance, if this was our original graph and this was the edge we cared about, an edge contraction would be like squishing these two vertices up here together. And if we do that, we get this triangle down. And an edge deletion would just be removing this edge altogether, which is it. So there's this theorem which tells us that if we care about finding the chromatic polynomial of a graph, then this is equal to the chromatic polynomial of this edge deleted graph minus the chromatic polynomial where we contracted this edge. Okay. Or equivalently, if I like move this last term over to the left-hand side, this is saying that the chromatic number of this original graph and this edge to contracted graph had to add up to this edge deleted graph. Now, what's the reason for this? Well, the reason for this, right, is because I've deleted one edge, I've lost one constraint from my original graph. And because I've deleted this constraint, this allows both of these two colors to be the same color, which is not the case when we had this edge present. So this is somehow overcounting these number of proper colorings, but it's only overcounting when these two vertices have the same color. So how do I deal with that? Well, I can just identify them together into the same vertex. And this is, well, by identifying them together, this is precisely when they have the same color. So this is why this formula holds. And so this gives you a way to program this, right? You can just program this recursively, right? In order to find this chromatic polynomial of a graph, you feed your graph into the computer, have it look for an edge. If it finds an edge, then you just have your computer recursively apply the same function to this edge contracted graph and this edge deleted graph. Okay? And then you do this until there's no more edges present. So now that we have a way to calculate this, maybe let's go back to our applications and see why this helps us in solving our two problems. So our first problem was the scheduling problem, right? We needed to find the chromatic number of our graph. So how does the chromatic polynomial help us find the chromatic number? Well, it turns out that the chromatic number is the smallest positive integer k, such that the chromatic number, or when we plug in this number k into our chromatic polynomial, it's not 0. Right? And why is that? Well, when we plug in numbers, or our polynomial is keeping track of the number of proper k colorings. So if we want to find the minimum possible proper k coloring of our graph, we just need to find the smallest positive number k that's not a root. So for instance, this is our graph that we saw earlier, and we saw that was k times k minus 1 times k minus 2 squared. So we see that 0, 1, and 2 are roots of this polynomial. So this tells us that our chromatic number, while 3 is, when we plug in 3 into this, it's not. So this means that our chromatic number is 3. Okay? So this gives us a way of like finding the chromatic number, right? It's like the smallest non-root of this polynomial. So our second application was to the Sudoku problem. And so remember, we needed to figure out whether there's exactly one proper 9 color. So one would think we could just plug in the number 9 into our chromatic polynomial for this graph, but then just check if this equals 1. But there's a slight problem, is that we only care about colorings that extend our already pre-colored vertices. Right in our Sudoku board, our grid was already populated with numbers, and we wanted to check if this is a valid puzzle or not. So we don't care about all colorings of our graphs, we only cared about the ones that extended these pre-colored vertices. So this doesn't quite show it, but we can just generalize our notion of the chromatic polynomial slightly, and we can get what we want. So this leads to the notion of a pre-colored chromatic polynomial. So let's say that we have some pre-coloring of our graph. This means we have our graph, and then some of the vertices are already pre-colored. So the pre-colored chromatic polynomial is the polynomial that counts not all proper colorings, but just the ones that extend our pre-color. So let's look at an example. So let's say that we have this graph here. We've pre-colored these two vertices, 1 and 3, both red. So what's the number of k colorings that we could have? Well, note that because I've already used up one color here, I only have k minus 1 options of how to color this vertex 2. And after coloring it, then I only have k minus 2 options for this color 4. But note that if I pre-color this graph differently, for instance, maybe I color this one or red and then this one blue, then this leads to a different recolored chromatic. And we still have the same nice property of a deletion contraction formula. So you can like feed it to your computer, it can sort of figure this thing out recursively. And this gives us a way to solve our Sudoku problem, right? We take our Sudoku puzzle, find its pre-colored chromatic polynomial, plug in the number 9, and then check if it's equal to 1. So this gives us a way of solving this puzzle, or this problem. Note that it doesn't give you a solution to the Sudoku problem. It just tells you whether or not this puzzle was or was not valid to begin with.
Sorry, I have a quick question. So for the writing that computer program to check, is it a one general program that you can put in all of them, or does it have to be specific for every different, does the programming part has to be different for different graph that you feed it?
It would be a general program,
Oh,
right? You
okay.
would have your program look for an edge. If it finds an edge, it like deletes the edge or contracts it, and then feeds these two new graphs back into the same function.
Okay, so it counts, it already take account of different types of graphs. Okay, thank you.
Yeah. Note that this graph or this algorithm can't be too fast because in general, finding the chromatic number of a graph is NP hard. And then even determining whether or not a graph is three colorable, proper three colorable in general is NP complete. So it turns out that these polynomials have some other nice properties in terms of their coefficients. So here are three graphs, and I've given their chromatic polynomial. And so maybe I'll give you a minute just to stare at these polynomials versus their graphs and see if you can find any pattern that you think might hold in general.
Well, first thing notice the 4 node and highest degree of polynomial is 4.
Ah, perfect. Uh, perfect. Yeah, so we see that the leading coefficient is always 1, and as you pointed out, the degree is always the number of vertices in our graph.
And the coefficients, the first two that doesn't have are those doesn't have the triangles are the symmetric two ways. And the 1, 3, 3, 1. I don't know if that's
Yeah, so yeah, in general, it may or may not be symmetric.
Mhm.
And then this comes from the fact that remember the fact that these two are the same came from the fact that all trees have the same chromatic polynomial, as long as they have the same number of vertices.
Right.
So one thing that you could notice,
Right.
maybe if I
Alternating.
gave you a little bit more time. Ah, yeah, alternating signs is another one, right? It goes plus, minus, plus,
Mhm.
minus, plus, minus, plus. And if we look at this number here, is 3, 3 versus this 5. And if we look at our graph, we see here we have 3 edges
Oh, okay.
and 3 edges. And then here we actually have 5 edges. And it turns out this is true in general. So the second term here is negative
Mhm.
1 times the number of edges.
Mm.
I think my next point is exactly what you said. The coefficient's alternated sign. And I actually forget what my last one. Ah, there's no constant term, right? Because 0 is always a root,
Mm.
because you can't color these graphs with 0 colors. But it turns out that there's another thing that's these graphs satisfy. So if I look at just these numbers and forget about plus and minus, so just the numbers themselves. So right here I have 1, 3, 3, 1. And this is the same thing, 1, 3, 3, 1. And this one here is 1, 5, 8, 4. We see that those numbers sort of increase to a point and then sort of decreases down. So we give this special property a name, which is unimodal. So it's unimodal if it sort of increases to a point and then decreases down. So for instance, 1, 4, 4, 5, 3, 2 is unimodal, right? It increases up to 5 and then decreases. Here we allow for weakly increasing, so I'm allowed for numbers to be equal. However, the sequence 1, 4, 5, 3, 4 is not, right? Because I go up to 5, then down to 3, but then I go back up again to 4. Right? So this is really meaning that I have a single peak in my sequence if I plotted them. So as a conjecture for a long time, um, that the absolute value of the coefficients of the chromatic polynomial are always unimodal. And recently, oh, so this is our example. So for instance, we had 1, 5, 8, 4. So recently, this was settled by Jun Ha in 2012, which proves Reed's conjecture. This is always true. And more recently, he sort of received the Fields Medal in 2002 for his work related to these structure coefficients. Now, the way he proved this was actually uh, used some quite heavy machinery from some algebraic geometry. So he somehow related some geometric object to these coefficients, and then using these tools from algebraic geometry, showed that they have to satisfy this property of unimodality, and more strongly, a property called log concatenation. So, my last, ooh, maybe 5 minutes or so, maybe let me give one uh, generalization of this chromatic polynomial. And for this is this notion of I'll need this notion of a symmetric polynomial. So a symmetric polynomial is a multivariate polynomials, and the variables, let's say x1 through xm, that does not change after swapping any variables xi and xj. So for instance, let's say that we have three variables, x1, x2, and x3. Then this polynomial x1 to the fourth times x2 plus x1, x3 to the fourth is not symmetric, right? Because in order to be symmetric, I would need to be able to change x1 and x2, and for it not to change, and x1 and x3, and x2 and x3. But for instance, if I swap x1 and x2, I get x1 times x2 to the fourth plus x2 times x3 to the fourth, which is not what our original polynomial. But for instance, this polynomial here is symmetric. So I claim that no matter I switch around these three variables, you're in this polynomial expression here, you'll always get the same expression back. Okay. So I claim that you've sort of already dealt with symmetric polynomials already. You just didn't realize it. And that's because if you take a normal polynomial and express it in terms of its roots, or really the negative of its roots, then how are these coefficients related to these negative of the roots? So there's this result by Vieta that says this coefficient of a to the n minus 1 is equal to the sum of all these roots, from negative of the roots. An minus 2 is equal to the sum of all products of these distinct roots. And for instance, a0 is a product of all the roots. And if you look at these expressions, note that they're all symmetric. Okay? So secretly, when you're dealing with roots or polynomials, looking at them in terms of their roots, you've sort of already been dealing with symmetric polynomials to begin. So why do we need this? Well, we're going to define a generalization of the chromatic polynomial called this chromatic symmetric function. So we're not only going to care about how many proper K colorings we have, we're actually going to care about which colors we used as well. And for us, right now, we're going to think of our colors really as the numbers 1, 2, 3, etc. Okay. So the chromatic symmetric function is equal to the sum over all proper colorings of our graph, where we keep track of every single color used in terms of a monomial term. So for instance here, let's look at this graph on 3 vertices. One way to color it, right, is this color 1, 2, 1, right? So remember, we're thinking of our colorings now as, rather than physical colors themselves, just as numbers. Because I only know a finite number of colors, but there's sort of an infinite number of numbers that one could use. So we could also color this 2, 1, 2, 1, 3, 1, etc. And then we could also color these like all differently, like 1, 2, 3. So we have like an infinite way of coloring this thing using these colors. And what is this chromatic symmetric function doing? Well, it's keeping track of the colors used in every single one of these. So this first term here, this x1 squared x2, corresponds to this first coloring because we used 2 colors of the color 1 and 1 instance of the color 2. So you have x1 squared times x2. And then here we have x1 times x2 squared. And here we have x1 squared and x3 because we colored 2 vertices 1 and 1 vertex colored 3. And then here, there's actually going to be 6 terms corresponding to x1, x2, x3 because I could shuffle these in any way possible and get a valid proper color. So it turns out that every term has degree n, number of vertices, and this is symmetric, right? If I switch the colors I and j, this will result in another proper color. So this is like some generalization of the chromatic polynomial. And if it's a generalization, then we should be able to recover the chromatic polynomial. So is this true or not? So I claim that the chromatic polynomial evaluated at k is equal to if I just plug in ones in the first k variables of our chromatic symmetric function, then zeros everywhere else. So for instance, this is our graph, this is our chromatic symmetric function. If I wanted to figure out what the chromatic polynomial is at 1, then I plug in 1 into x1 and 0 everywhere else. But every variable or every term in this expression contains more than just x1. So all of them will cancel, so we just get 0. But for instance, if I do 2, this means that I plug in 1 into x1, 1 into x2, and we just pick up these two terms here, which gives us this 2. So this tells us that there's two colorings of this graph with two colors. And because this is exactly how we defined our chromatic polynomial, this means that we can recover it. And our chromatic polynomial was described in terms of the number of ways um, that we could proper color a graph with k color. Now you might be wondering, okay, can we get more with this chromatic symmetric function than we did with the chromatic polynomial? And in fact, we can. So it's a conjecture that the chromatic symmetric function differentiates trees. So remember, the chromatic polynomial of a tree was always the same, right? Meaning that it couldn't tell trees apart. But by upgrading it to this chromatic symmetric function, this gives us a way, conjecturally, of being able to differentiate trees. Okay? And this is still open, but it's been verified up until 29 vertices. And there's many other open conjectures related to this upgraded version of the chromatic symmetric function. So maybe let me stop here.
Thank you. Thank you so much for the very interesting talk. Let's give Dr. Joseph Pappe a round of applause and then we'll take questions. Thank you. All right. I have a question. Do you have a quick example of how the chromatic symmetric function identifying trees? Just maybe just two simple trees. And
Ah, mm, I don't have one off the top of my head. But there's been work in like I think
mhm.
it's been shown to prove differentiate all caterpillar trees. These are like path graphs where you have like little legs sticking off.
Ah, okay. Okay.
So
So it
this has been
identifies
proven.
different types of trees or what
Or
specific
and
feature about trees it's differentiating, if we know.
so basically it's saying that if I give you two different trees, then they have different chromatic symmetric functions.
Ah, okay.
Meaning
Okay.
that if I gave you the chromatic symmetric functions to begin with, you could tell which tree it came from.
Okay.
Yeah,
Thank you.
that's conjecture.
Interesting. Right. And you said it's verified up till
I
29?
think it's like 29 vertices. It was
29 or
the
something.
last, yeah.
Okay. Has there any progress made on the proof, or is it purely computer verifying up to 29?
So that one's computer verifying. There's been, as I said, there's been like some classes which been are known to be distinguished among themselves. So
Mm,
that like these caterpillars and maybe some other families.
mm,
Um, and there's conjectures about features about trees that you can extract from these polynomials that could sort of help you differentiate trees,
Okay.
but nothing, nothing in general.
Okay. Thank you.